Hi, this is John Martin, President of Offshore Robotics. I'd like to share with you a video here of a system to perform robotic riser make and break. This system was developed to perform tasks that are currently done with people. And the reason or the need for this was that the people are in harm's way performing tasks underneath loads and working with very heavy objects, as well as torque wrenches that can become jammed and become a dangerous object to the people involved. So this is the reason for or necessity actually to automate this process. The system has two robots on the port and starboard side of the system. Attached to those robots are two tools. We call them multi-tools. They have cameras embedded inside of the tools, and they have sockets to manipulate devices as well as the bolts and to run up and to loosen the bolts. So right here you'll see the cameras taking pictures of the riser position. That's important because the riser will move during the riser makeup process. After the hull cover is installed by the port robot, the system then will grab two stabbing guides. The stabbing guides are used as a help from the driller to position the upper riser onto the lower riser. The stabbing guides are inserted approximately 5 rotations. After the stabbing guides are installed, then the cameras go to work, or the robots go to work with their cameras to locate the 6 bolts that will be installed into the riser flange at a later time. Once the upper riser is in position by the driller and ready for mating up to the lower riser, the port robot will remove the hull cover, giving access for the upper riser to be installed. And if you notice, a lot of the robot moves are made such the robots can work while there's a load above them. So we don't have to pause operations on top of the spider. They can still do tasks as the drillers are manipulating and moving the riser sections into place. First operation is to remove the stabbing guides so we can then install the bolts. And if you remember, the bolts were already located with the camera system, so the orientation is known for the 6 bolts that will be installed. So the servo motors that rotate the multi-tool socket, they are already matched and synced up with that bolt hex. So the tool will simply go down over the top of the bolt, actuate a fork underneath the bolt head, and then be able to lift that bolt out of the bolt bin and put it into the riser flange. As the last bolts are being inserted here, you can see a little bit of the multi-tools compliance, this thread compensation compliance. It's used to match up the robot motion with the thread engagement as we're tightening and loosening the bolts. We also use this for fault detection. So if for some reason the bolt head did not go into the hole, it will actuate that switch, and then we'll be able to do a series of moves to be able to get the proper alignment of the bolt with the hole. Once all the bolts are installed, we'll change to our high torque tool. The torque tool is a hydraulically operated tool. We can get up to 36,000 foot-pounds of torque. Typical torque on a riser flange like this would be 18,000 foot-pounds. So once both robots are in position and ready to torque, they will start that operation. The system is set up so that both robots will be torquing or must torque at the same time. That's important for proper torquing of the riser flange so that we know we're getting equal torque on each side of this riser as we perform the torque. The robots themselves don't really know where the hex of the bolt is with this torque tool because it is hydraulically rotated. So what it does is use a feature on the robots called soft float. And soft float pretty much allows the robot itself, the whole 6-axis arm robot, to be compliant. And so as the robot is rotating its socket above the bolt head, it is trying to kind of put a force downwards to engage over to the bolt head. And then once the socket matches the bolt head, it does slip over the top of it, as you can see there, and then it will soft float into the reaction arm and then apply the high torque. As this last bolt here is being torqued, you can talk a little bit about the components of the torque wrench itself. We have an intensifier to intensify our 3,000 psi input pressure, hydraulic pressure, to around 10,000 psi output hydraulic pressure. We're also detecting the torque of the bolt based upon the pressure in the wrench. So we have a sensor that has given us the actual hydraulic pressure inside the cylinder of the torque wrench. And we're monitoring that, so as it intensifies, the pressure slowly increases, and at set pressure, we know the desired torque so that we can stop that operation. And we do a double confirmation that we're at torque. All the torque values of the riser makes process is recorded and can be kept and reviewed at a later time. So once the bolts are torqued, the riser make process is completed. The driller is free to take the load off of the spider and open the spider jaws. As this is happening, the robots will change to their multi-tool for the next operation. So now we'll show you the riser brake process. First step that happens here is the driller lowers the riser into the spider jaws and closes the spider jaws, and then we'll release the weight of the riser on top of the spider jaws. So now the robots will take pictures of the position of the riser bolts for the riser brake process. This is important because once the riser is manipulated into the spider jaws, it can move maybe about a half an inch and rotate a couple degrees. So we need to know where the bolt positions are in order to position the torque tool and the multi-tool over the top of them and to engage the sockets into that bolt. So the tools are now changed to the torque tools. This torque tool design can simply be rotated 180 degrees to go from torque to untorque. So there is no changeover at all on the tool. A reaction arm, you notice, is now using the adjacent bolt on the opposite side, so we don't have to move the reaction arm at all. You see there the fault response software kicked in where the torque tool did not engage over the bolt. And what it does is it lifts up, it cycles the wrench, and then it will try again rotating the wrench using soft float to engage over the top of the bolt. The system uses the pressure sensor to detect when the bolt is loose. So we know the pressure will intensify to a certain PSI as there is quite a bit of torque to loosen the bolt, and that will diminish as the bolt is easily rotated. So the software detects that. It's not using a cycle count or anything like that. It's actually looking at the pressure inside the torque wrench to determine when that bolt is freely spinning. So changing from one tool to another, the system uses a quick change device. It's an ATI quick change device that is able to carry electrical connections for our servo motor, for our sensors, power, and it also carries the hydraulic fluid and pneumatics that we use for actuating our bolt retainment fork and for the tool changer itself. So now that the bolts have been loosened by the torque tool, we will go and take a picture of them to find, again, the position of the bolt, just in case it moved during the untorquing process, and the rotation of the bolt. The rotation is important so that we can match the socket up with the hex of the bolt to engage it over the top. As you can see, the robots can run unparalleled. They don't really have to be synchronized during their individual tasks of unthreading and moving the bolt. They can work pretty much independently doing this. The only time they really sync up is during tasks that are necessary to sync. That's during the torquing process or if they are untorquing a bolt. We want those robots to move 180 degrees from each other. Well, thank you for watching the video with me, and if you would like to get more information about the system or anything we're doing here at Offshore Robotics, please feel free to contact us at info@offshorerobotics.com.